All right, team. So, what we are looking at today is, we're still looking at number 6. So, drawing those Lewis structures and identifying the shapes. So, now we're looking at the shape component of that. See on the back, see if we have anything on here about shapes. Draw the Lewis structures. Oh, here we go. So, on the back page, just so you guys are aware with where these shape questions are going. So if you guys remember last week, the achieve criteria was drawing the correct Lewis structure, identifying the shape as well is another thing for the achieved. For the merit then, and for the excellence, you are looking at justifying why you have that shape and why you have that polarity. What I find this year in comparison to last year is that this year they're not going to be as separated as a question. They tend to combine shapes and polarity together. So if you remember last year, they would give you a molecule they'd have to explain the shape for, and then some separate molecules they have to explain polarity for. In this case, they kind of combine it into one question, and it's briefer because they have a different, like, new other questions that are going to be given instead. So when we're looking at the merit level, you can explain one molecule correctly, the shape and polarity, or both molecules are partially explained. So most of these questions, they're going to give you 2 molecules, and they're going to ask you what is its shape, what is its polarity, and justify why. So multiple ways you can get that merit point. They are very intertwined, these 2 things, so you kind of keep that in mind. And then the excellence is being able to explain both molecules, both shape and polarity. So like I said, it's a very kind of intertwined question, whereas last year it was more separated. So just kind of keep that in mind. We're starting to look at the shape component of it, and then Friday we'll look at the polarity one. I figured I shouldn't overwhelm you guys. Looking at this checklist on the frequency they asked that question. So you can see shape of molecule and shape of ion. So they could ask you the shape of the ion as well. Same sort of idea with the Lewis structures. You use the same sort of justification. So we're looking at those 2 today. And they have asked that recently in 2020. And then there's kind of a drought of when they asked it, and then they asked it in 2016. So it may or may not come up as like a direct thing. But most likely what it'll come up as is, in this case, shape and polarity, which is together, if you guys see it. So you see the last 3 years here, they've done that. So do keep in mind those things are integrated together and not really as separate ideas. So do kind of watch out for that. I think that's all that I have for that. So let's kind of refresh what we do when we're trying to think about shapes and the reason for that. So if you guys remember from last year, there were 2 factors that you were looking at to determine shape. The first one is the number of regions of electron density, or the number of electron regions around the central atom. So we're only concerned about the central atom when it comes to the shape. That's the first thing you look at. And then you just do a little count. So like, how many are there? Last year, you guys only had these 3 options. You had 2 regions, 3 regions, or 4 regions, if you guys remember that. Yeah. And that last year, you were primarily looking at bond angle. So you looked at the bond angle first, and then you looked at the shape, if you guys remember last year's question. And then after you looked at how many regions of electron density, you then asked how many were bonded and how many were unbonded. So when we're looking at last year's examples, keep in mind that when we are thinking about regions of electron density, we're thinking about bond and unbonded. So in this example, this has 1, 2. This one has 1, 2, 3. This one has 1, 2, 3 as well. This one has 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So we then grouped them based on their regions, and by their regions, we then had a bond angle that was associated with it. Second thing you looked at was if it was bonded or unbonded. So in this case, all three of them were in bonds, resulting in a triagonal planar, whereas in these two were in bonds, but this one is a lone pair, resulting in a bent shape. So that's what we're looking at when we were thinking about that last year. And if we want, we can look at the notes that we did on Thursday when you guys are doing some revision. So if we're looking at my ammonia right here, there are 3 regions that are bonded, 1 unbonded. So 4 regions. So that would be 109.5. And then because only 3 are bonded, 1 unbonded, that resulted in a triagonal pyramidal shape. That's how you guys were doing the processing last year. Does this ring a bell? Wait. All right. Cool. Moving on. Wait. I'm just kind of showing you an example of what you guys did last year. It's unlikely they will ask you a simple molecule because they've already asked that question last year. So keep that in mind that these shapes are unlikely to come up again. Cool. Keep going. Keep going. No, still writing this down. Okay, moving. It's okay. No, I'm happy for you guys to write things down. I want you guys to write things down. All right. Ready for some new shapes. So, unlikely they're going to ask these guys. Very likely they're going to ask these guys. So this is like we were talking about the extended octet. Now we can go past 8 electrons. And because we're going past those 8 electrons, we now have to think about some new shapes. The good news is, even though they have bond angles on the bottom, I have never seen them ask a bond angle question. So, and if you look at the list of the audit questions, there's never been anything on this list that says bond angle. So that's the good news, is that there's no justification for bond angle anymore. So that's why they've kind of collapsed the shape and the polarity question together, because they removed the bond angle question. But do kind of keep in mind, when you are justifying shape, you will be justifying it with the VSEPR theory. So VSEPR theory, if you guys remember, was regarding that valence shell electron pair repulsion. I think that's what it stood for. What you're thinking about there is that these electrons, they're trying to maximize the space apart from each other to minimize repulsion. My space to minimize repulsion. So that's why they take the shapes that they do. It's so that way that they're not putting those like charges together. Repulsion. Yeah, because the electrons are negatively charged. So like of electron, or sorry, I'll add the note, not likely to ask about bond angle this year. So don't worry about memorizing that. It's not a good use for your brain space. And I guess the reason why is because there's so many complicated bond angles, because there's usually multiple bond angles because of the lone pairs of electrons. All right, so 5 regions or 6 regions, and then same thing that you are dealing with. Are those 5 regions all in bonds, or are there some that are not in bonds? So if I have all of my 5 regions in a bond, and there's no lone pairs, I would get a triagonal bipyramid shape. You're gonna have a lot of new shapes to remember. So I'm trying to kind of help you formulate what they are. You see how this is a triangle? And then bipyramidal, you have 1 pyramid on the top, 1 pyramid on the bottom. So it looks like the, where are you? It looks like the triagonal pyramid, but there's two. Okay. The next one is you have one lone pair of electrons and four bonded. We call that a seesaw shape. Now we're getting some funny names. The way I like to think about it is if I flip it on this side, those are the two anchors to the seesaw, and the other two are the little benches that people sit on. So that's why that looks like a seesaw. I'm so sorry. These shapes are terrible. All right. If you have two unbonded pairs of electrons and three bonded, they call that one T-shaped. It looks like a T. So basically, like I removed one of the legs here. And if I remove one of the legs, then this turns into a T. All right. And then if I have three regions of electron density, they come center around that central atom. And then these two are my bonded regions. It goes into a linear shape. Straight line. Okay. I know. I'm just like, right. If we have six regions and all of them are bonded, we call that an octahedral. Similar name to the tetrahedral, but now octahedral because we're doubling it. In this triangle, you have four sides to it, or this pyramid, I should say, has four sides to it. So tetra, 4, octa is 8. So you have four sides of the triangle on top, 1, 2, 3, 4, and then 4 on the bottom, octa. It's just like, anyway. If one of those if one of those regions is now a lone pair of electrons, we got rid of that there. We're basically getting rid of the bottom half of the pyramid. And so now we just have a square pyramid. This one is different from this one because you notice that there's 4 on the bottom. So it's like a square that has a pyramid going up like that versus having just like the 3 going up. So that's our square pyramid. And then if you have two unbonded regions, then you have a square planar. It looks like a square and it's flat. Planar means flat. You guys have seen this before with the tetrahedral. There's a, sorry, not a tetrahedral, triagonal. That one's the triagonal planar with the triangle flat. This is the triagonal pyramid where the pyramid is built in 3 dimensions. So those are weird shapes. So you have these shapes that are going to probably come up. It's very unlikely they'll ask any of these shapes this year. So let's look at some of our examples. It's mostly just a game of memorization. So if you look at the Lewis structures we did last lesson, this guy has 5 regions of electron density. All 5 are bonded. So if I was to use my table, 5 regions, all bonding pairs, this would be a triagonal bipyramid. It because you're not going to be given this table on the assessment. Yeah, that's why I'm saying it's useful to kind of think about them as shapes and what you would have logically speaking. So like when I said triagonal bipyramid, like you're getting the triangle and then 2 bits of the pyramid. So here's my triangle and then like, oh man, it's not really good to draw in 3 dimensions on a 2-dimensional plane. Never mind. All right, this one over here, we have 1, 2, 3, 4, 5, 6 regions of electron density. 2 of them are unbonded, 4 of them are bonded. So 6 regions, 2 non-bonding pairs. So this one will result in a square planar. Yep. No, you don't have to draw it. And you got to justify the shape. So you would justify the shape using Vespers theory. So you'd be like, because this molecule has 6 regions of electron density, 4 of which are bonded, it's going to separate to maximize the space of the regions of electron density to minimize repulsion, resulting in a square planar shape. Okay. You okay with that? All right. This guy and this guy will actually result in the same shape. These are 1, 2, 3, 4. 1, 2, 3, 4. Remember, the double bond is counted as one area. So these are both tetrahedrals. Unlikely that's going to pop up, but if it does, that's what that one looks like. This guy over here, 1, 2, 3, 4, 5, 6 regions, all bonded, octahedral. That's all you gotta do. And then when you justify it, remember how many regions of electron density, how many are in bonds, VSEPR theory, therefore my shape is blah. So VSEPR theory is just saying that we are, because these are all negative areas, or sorry, negatively charged areas, the like charges repel. So they're going to repel to maximize the space between them and to minimize the repulsion. So they're just basically trying to separate so that way they're like as far apart as possible without crashing into the next area of region of negativity. Okay. Cool. Questions, concerns, comments? Nah, pretty straightforward, I figured. All right, so for you guys, I would like you, we've done the notes, short and sweet. SciPad pages 35 to 38 practices material. If you are not confident with it, or sorry, if you're not confident with Lewis structures, I would say do Lewis structures first and then do this, because in the event that they tie the Lewis structure question to the shape, you need to draw your Lewis structure correctly. Otherwise, it snowballs and you can't get the shape correct. Does that make sense? Should I repeat that one more time? If you don't draw your Lewis structure correctly, it will snowball and you will get the shape wrong. And so instead of losing 1 point, you'll lose 2 points. So take your time and learn your Lewis structures. So if you're not confident with Lewis structures, go back to that first. All right, cool. That's it.